And welcome back. Let's go ahead and explore our algorithm just a little bit more. Of course, we have our binary search here, which we, of course, know works excellently with recursion. However, just for comparison, let's also look at a linear search, which you can see is much simpler and uses a more iterative approach. We, of course, just have a simple for loop that's going to traverse through. If it finds where it is in that array, it's going to return us that position. And if it's not there, returns -1. Again, very similar to what we have here, except this is done with a linear approach. Let's go ahead and test this out with a program that's going to allow us to get 10 integers. We're going to fill that into an array, and then we're going to print it just so we can test to see what this actually looks like. So let's go ahead and enter in 10 integers. I'm just going to go ahead and fill it with 10 random integers. Doesn't matter what they are because, again, we want this to be random. And you can see we get 1, 3, 2, 6, 5, 4, 2, 8, 4, 2. Now, we want to look for a number to be part of the array. Now, one thing you'll notice is that this program is first going to attempt to search before it is sorted. If you recall, a binary search requires a sorted array. So what happens if it's not sorted? What's that going to do? And then, of course, we're going to sort that array and then reprint it just so we can test to make sure that it is sorted. And we're going to then attempt to do a linear search and a binary search again. So let's go ahead and input in, let's say, 8. Or let's go ahead and just do 8. Sounds good. And you can see with 8, it works good. 8, you got 7 and 7. But what happens now if I were to put a different number after that 8? That's no longer the largest number there. All right, so let's go ahead and run this. And again, I'm just going to enter in some random numbers here until this is filled. And now let's go ahead and search for this 3. All right, so I'm going to go ahead and put in a 3. And uh-oh, I got a 7 and a -1. So the other one worked simply because we had a value that was large enough for the binary search to say, here's where the middle is. It's got to be the biggest value. We'll go from there. But here, because it sees this 9, it says, well, that's the biggest value. I don't need to look past that point. The linear search knows to keep looking because it's going to go through the whole array. However, the binary search says, oh, I don't know what to do here. And so we just get the -1 because it doesn't know that this 3 still exists out here. But once it's sorted, you can see that how much nicer that turns out here because we get the correct value. Now notice the linear and binary sort do work the same. However, are they as efficient? Let's go ahead and quickly just add a variable that's going to allow us to keep track of the number of hops here. So we'll just call this int counter, and let's set this equal to 0. And what we want to do is when we're going through this method, and every time we iterate through this loop, let's just call counter plus plus. And we're probably going to have to make this static here so we can reference this because it doesn't know what to do with itself right now. So it cannot make a static. Yep, so we got to make a static int. And so we're just going to go ahead and add that modifier. And we're actually going to copy that over to our binary search as well, just so we can, again, kind of keep track of things here. Now, what we want this to do is to exist similar as we saw before, and we want to, anytime it goes into this else statement here, because we of course have that chance to call this method, we want to increase counter. And so now what we can do is we could print out what that is. So for example, if we were to come to here and just say, after our linear search, we know that this doesn't work here. So I'm not even going to bother printing that out, but we know with our once it's sorted, we can go ahead and see just how many iterations that went through. So we could do linear search dot counter, and we could just print that out. And then I'm just going to print that again, but let's print now for the binary search and print out that counter. And so if we run this again, so let's create a couple random numbers here. Okay, now this one, of course, if we look at this, if I enter in, let's say 6, we should, of course, we get an error here with the -1. That's great. But now we can see down here we got 7 and 7 because the binary search did what it's supposed to do. And you notice now we have a 12 and a 6. Those are the number of hops it took to go through that algorithm. And even at this small data size, at size 10, you can start seeing how the linear sort is already less efficient than that of the binary sort. Notice this was half the size. It said it took 12 hops for it to complete that algorithm with the linear sort, but it only took 6 hops for that binary search. And that's because, remember, this is going to cut that stack size in half. So it only had to search 5 times and do 5 different iterations for that to happen. So a quick way to kind of demonstrate that, yes, our binary search is more efficient than that of our linear search because it has less calculations for it to perform. And it makes sense because, again, remember, you're only having to search technically half of this array because we know we can cut this half. Boom, there it is. And now I only need to search this part of it to see if that number exists. Rinse, repeat, till I find the number I want. And if it's not there, well, return -1. But hopefully this has given you some more context as to how to create a much more robust program here with your different searches. There are, of course, going to be times when we want to do something more linear. As we saw, if our array is not sorted, then a linear sort might be more applicable. And there might be times when you don't necessarily want to sort your data. However, there might be ways around that. For example, can I make a copy of my data, sort that data so the original data is preserved, and then do analysis on the copy of that data to get what I want? There are ways, of course, to address all these different things. These are getting into higher level thinking of how do we design our programs? What do we need to accomplish it? What kind of things are we going to have to do trade-offs and stuff like that? And I think this is going to lend itself really well to, as we start looking at different types of algorithms, what these are going to do for us. And let's not just kind of limit ourselves to, for example, searching for a number. What about if we want to start to talk about sorting those lists themselves? We, of course, have up to this point probably 2 main sorts that we have looked at, which is the bubble sort and the selection sort. The bubble sort, of course, is really easy and has a slightly worse, but not too much runtime than that of a selection sort. But there are other things that can be faster, because for us using 10 numbers, this is not bad. But what if we had a sort, let's say 10,000 numbers? This is when you're going to start noticing a lot more slowdown. So is there ways that we can start developing programs that are better? And the answer is yes. And so recursion is going to help us a lot as we start to examine these next things.